Okay, so we're going to go over these three examples. I actually recommend you stop, pause the video a little bit, and see if you can do one or two of them. You may want to leave this if you want for me to go over it, this second example, because this one has non-zero initial conditions. But the left and the right hand side, you can try on your own a couple of them. On the one here, the third example, I have essentially three types of three ODEs into one, right? I mean, the left side is the same, but f of t can have, let's say, three different values. So you have essentially three differential equations nested into one of them, just to emphasize how easy it is to actually do that if you write the answer with the convolutions. So pause for a moment and give it a try. And now let's check to see if you got the right answer or not. So let's start with this one here. This is a typical example that emphasizes the advantage of using the convolutions, because if you look at the right hand side, the tangent of t, we don't actually have a formula for the Laplace of tangent of t in the table. I mean, you could do it with the maple, but that's not an easy integral anyway. Nevertheless, we don't have a formula for it in at least in the table I provided. But with the convolutions, we don't need. That's the key thing. You won't need ever to actually find the Laplace transform of the right-hand side. Doesn't matter what f of t is, you won't need to find its Laplace transform. Again, provided that you write your answer with the convolution. You may still have to do some work. So in this case, when you take the Laplace on both sides, so I mean, you can start with the transfer function right away, right? So I mean, if you have zero initial conditions, you can start right away with the transfer function, which remember is just 1 over the characteristic polynomial in S. You can always do that if you have zero initial conditions. If you don't, you got to carefully write down what L of the left side looks like. Because again, the reason the left side is just the characteristic polynomial is because you have zero initial conditions. So linear zero initial conditions, I can start right away with the transfer function, and all I got to do is to find the inverse of it, which is the so-called impulse response. On the other hand, that's not immediate here, right? Because we need to split this into partial fractions. A over s minus 1 plus b over s minus 2. I hope you know the drill already for this one. So 1, the numerator on the left, should be equal to a times s minus 2 plus b times s minus 1, which combines into a plus b times s minus 2a minus b. So write a little system here. A plus b ought to be 0, right? Because there's no s on the left side. And minus 2a minus b should be 1. Add the two, and you get minus a equals 1, or a equals minus 1. And from the first equation, obviously we get b equals 1. So your transfer function h of s is a over s minus 1, that's minus 1 over s minus 1, plus b over s minus 2, which is 1 over s minus 2. And then finally the impulse response, h of t, the inverse of big H of s, which is minus e to the t plus e to the 2t. So the hard part is over, right? I mean, that is the impulse response. And from the theory we discussed before, we know that the solution of the initial value problem is the impulse response that you just found, convolution, whatever the right hand side is, which is tangent of t. Didn't have to find the Laplace of tangent of t. Okay, so I hope that's clear. Let's move on now to the second example. You really have to be careful, right? I mean, this standard approach, transfer function, impulse response, solution, again, works if you have zero initial conditions. Here we don't, so therefore we have to carefully take the Laplace on left side and apply the formula, so linearity property first of all, notice that I didn't specify what f of t is. Let's just write the Laplace of it as we normally do by big F of s. You will see that even in this case it won't matter what it is, because you won't actually have to take this, compute this Laplace transform of little f of t. But let's denote Laplace of little f as big F of s as we normally do. And here, let's apply the formula. What's L of y double prime? That's s squared big Y minus s times y of 0, okay, which is 0, minus y prime of 0, which is 1. And then finally plus 4 quantity s times big Y minus y of 0, which is again 0. That's the Laplace of the right hand side, which is big F of s. So notice that, really pause and look carefully here once we simplify this. When you pull out y, sorry, this is a mistake. I'm sorry, just a second. This is not y prime. I just put the Laplace of y prime because there is no y prime, obviously. Sorry about that. So L of y double prime, that's what it is, and then this is just for big Y. So what I wanted to say is that if you look carefully, when you actually pull out y, you still end up with the characteristic polynomial, which is s squared plus 4. So you still end up with something like this, right? With the characteristic polynomial times big Y, but you have some additional terms. In this case, just minus 1. So you have some extra stuff created by these non-zero initial conditions. If this was also non-zero, you have more than one term here. So once again, you still have the characteristic polynomial times y, but some extra terms. So now when you actually find big Y, you ought to move these extra terms on the right hand side. And then divide by s squared plus 4, which gives me pretty much what I had before, but again some extra stuff. So what's the difference between zero initial conditions and non-zero initial conditions? If you had just zero initial conditions, you only end up with transfer function times big F of s. If you have non-zero initial conditions, you still have that, but some other stuff here. So that's not a huge problem because you could still use convolution. I can still use the convolution for this part. So when I take the inverse of this, so that's the inverse of 1 over s squared plus 4, and I can still use the convolution for this product, and I can still bypass finding the Laplace of little f of t. That's the key thing. I can still bypass finding this because this reverts back to the original little f of t. Now, inverse Laplace of 1 over s squared plus 4, you gotta multiply and divide by 2, so that's 1 over 2 sine of 2t plus 1 over 2 sine of 2t inverse Laplace of big F, which is just little f of t. So the main advantage, one of the main advantages, of solving this via Laplace transform still holds if you have non-zero initial conditions. You can still bypass finding the Laplace of little f of t. The only thing is to be aware that you'll have some extra stuff, and you'll have to be more careful when you solve y from this equation in the beginning. So finally, the third example, this one starts with zero initial conditions, so I can just start with the transfer function. But here we have like 3 equations into one, right? But because we know that my solution always looks like h of t convolution f of t, I need to just produce that h of t, the impulse response, and then I just do the convolution with whatever f of t is, and I can solve essentially 3 equations in one setting if you want. So what's the transfer function? Well, the transfer function is 1 over the characteristic polynomial, 1 over s squared plus 1. Impulse response is the inverse of that. which is just sine of t in this case. So now I can provide the solutions for various values of f of t. If f of t is e to the t, the solution is sine of t convolution e to the t. If f of t is cosine of t, y is convolution between sine and cosine. And finally, if you can keep on going, right? I mean, if f of t is t squared, y is the convolution between sine of t and t squared. So this is in a nutshell probably the another advantage of the convolution way of writing the solution. You can have this very nice and standard way of providing the solutions for various forcing terms, right? I mean, if the left side doesn't change, you can keep on changing the right hand side by simply changing this right term in the convolution. So that concludes the chapter on Laplace transform, and I hope you found it interesting. We're going to move on to systems next time. We're going to focus on just on 2x2 systems. So on the next lecture, we're going to discuss some general aspects of how a 2x2 system looks like, what a linear system looks like, homogeneous or non-homogeneous. We're going to follow the same framework. And also we're going to, in the beginning, we're going to pay attention to the matrix notation of systems, because that's the most efficient way of studying linear systems via matrix notation and matrix operations. So that's it for this lecture. I'll see you soon.